All right, so this is our last video in Unit 1. We're going to talk about periodic trends. This should also be reviewed. You should remember this from pre-AP chemistry too. So remember, if there's anything you don't understand, please make sure you make use of the long list of video resources that are posted in your notes, okay? All right, so periodic trends. So the periodic table is arranged by the atomic number, but there are certain trends or patterns that we see when we look at it, when we arrange it that way. So the first is atomic radius. Radius, remember, the atomic radius is half the distance between two identical atoms that are covalently bonded together, or it's simply the distance between two bonded atoms, okay? So what we notice with that then, the trend or the pattern that we see is that as you go across the periodic table, the atomic radius decreases, and as you go down, the atomic radius increases. So it's important for us to know these trends, but we also need to know why they are what they are. So it's not just a matter of saying, it gets smaller as you go across and bigger as you go down. We're going to look at why does that happen, okay? All right. So the ionic radius would just be the distance or the size of the cation or anion. So cations are where electrons are removed. Okay, so in this case, electrons are removed. And so that means that they are smaller than their parent ion. And they're smaller than anion. So, and most of these are going to be metals. So metals are the ones that can lose their electrons the easiest. So when they do that, they will be smaller than the parent ion. They will also be smaller than anions will be. And the reason for that is because if you're taking those electrons away, you have fewer electrons, but a greater number of protons. So you have a bigger positive charge, a smaller negative charge. That means that positive charge is going to draw those electrons in closer than they had been before. Okay, so because you have a greater, we call it a Z effective, but we have a greater positive charge than we do negative charge, that positive charge draws those electrons in. For the anions, this is where we add electrons, and they are going to be bigger than their parent ions, and they're going to be larger than cations. Most of these are nonmetals, and the reason, again, we have to know why. The reason for this is because you're adding more electrons in. Like charges repel each other, so those electrons are going to repel each other and get further away. Okay, so the electron is going to get bigger. It's going to get bigger because of electron repulsions. Okay, over here for the cations, this is going to get smaller because you may be in a lower energy level, and also because the positive charge is going to draw them in. Okay. All right, so predicting ionic radiuses, they're going to go down. So they're going to increase as you go down the periodic table. So again, these are our things that will become anions. So as you go down, they will get bigger and bigger and bigger. They also are going to increase as you go across. The ionic radiuses will increase as you go across, and will increase as you go down. Mainly, you're increasing as you're going down because you're adding more energy levels to that atom. Okay. So here is all of your metals. So all of your metals as you, the radius increases here because the more electrons you take off. No, that's not right. Never mind. Okay. So the size increases as you go down and increases as you go to the left for metals. For nonmetals, increases as you go down, increases as you go to the left for the nonmetals. Okay, ionization energy, that is the energy required to remove an electron from an atom. How much energy does it take to pull electrons off? This is always endothermic. It's endothermic because we are having to put energy in to get this to happen. So ionization energies are going to increase as you go up and as you go over. So these elements here at the very top have the highest ionization energy. Okay, because they do not want to have electrons removed. Things over here, down here at the bottom, are going to have a low ionization energy because they do not mind having the electrons removed. It doesn't take as much energy to pull the electron off. Okay, so this ionization energy and atomic radius are the opposite. Opposite of atomic radius. Okay. All right, so this next slide. So this next slide is just giving us some examples of these. You can see that, oops, here's the first ionization energy for sodium, and then here's the second one. Okay, so taking that first electron out of the valence shell is really, really easy, but taking the electron out of a full shell, that second energy level is full, at that point is very, very difficult. Okay, same with magnesium. The first one is pretty easy. The second and third ones are much, much harder. Because you are, like for silicon, okay, silicon has 4 valence electrons. So you can see it's easy to take off the valence electrons, but it's much more difficult to take off what we call the core electrons, or the electrons that are in those full shells underneath. And the same for here. Okay, all right. So reactivity is the next trend that we're going to look at. No, it's not, or it's not supposed to be. Okay, well, we will. Reactivity, you can see that it increases as we go down. Increases as we go down and as we go across. So these metals are much more reactive over here. And these non-metals, it's the fluorine that is the most reactive. Okay, and this is based on ionization energy. Okay, so over here, we're increasing as you're going down because of ionization energy. Okay, these things here at the top have a lower ionization energy. So they are going to react faster. It's going to be easier to remove that electron. And so that's why they have a lower ionization energy, because it's easier to remove the electron, so it'll be easier for them to react. Over here on this side, and we'll talk about electron affinity in just a minute, but these increase because these have your highest electron affinity over here. As you go up to the top, those have the highest electron affinity. These are things that want to gain electrons because they want electrons. Okay, electron affinity means how badly does it want an electron? Okay, so fluorine really wants an electron very, very, very badly. It has 7 electrons. If it had one more, it would have a full shell. So it's going to do anything it needs to do to gain that one more electron. So we say it has a very high electron affinity and therefore a high reactivity. Okay. All right, so here's just a little chart to look at reactivities of metals versus nonmetals, metals are more likely to lose electrons. Nonmetals gain electrons. The largest metals are the most unstable. They react the easiest. The large metals are unstable because their ionization energies are very low, so it's very easy to remove electrons. The larger atomic radius means that the valence electrons are further from the nucleus, and since the valence electrons are further from the nucleus, it makes it easier to pull off that electron. Large metals have a low Z effective, which increases their reactivity. On the other hand, nonmetals are pretty much the exact opposite. Small Z effective, most electronegative, so they want those electrons. They attract electrons very easily. The smaller nonmetals are more unstable because they really want that electron. It makes it easier for them to attract electrons than other atoms. Okay. All right, Coulomb's law. I seem to have lost my electron affinity slide. Well, I'm sure it'll come up. All right, Coulomb's law. Coulomb's law states that the force of attraction between two charged particles is proportional to the charges and then to the distance between them. So it's directly proportional to the charges of those two particles, but it's inversely proportional to the distance between them squared, okay? And K is just a constant. So Coulomb's law is what helps us to explain why some of these trends exist, okay? So opposite charges attract, like charges repel. Opposite charges attract, like charges repel. Come on. No, that's not what I wanted. There we go. All right. Electrons are attracted to a positive nucleus, and then electrons repel each other. So the greater the numbers on the charges, the greater the force of attraction. So magnesium 2+ is more attracted to chlorine than is sodium, because magnesium has a greater charge on it than sodium does. So magnesium really, really wants to react with chlorine because it has it's missing 2 of its electrons, okay? So that greater charge means it will be more attracted to the chlorine. The closer the particles are, the greater the force. So the smaller it is, the greater the force of attraction. If they're very, very far apart, then they're not as attracted. So sodium is more attracted to chlorine than potassium is, because sodium is smaller than potassium is. And so its nucleus is closer to that, to the valence electrons of chlorine. Okay, there's a video link there that in the PowerPoint you should watch on Coulomb's law. So just remember, this helps to explain why some of the trends happen the way they do. Okay. So looking at explaining some of these trends. Come on. Z effective, or the effective nuclear charge. The more positive the nucleus, the more attractive force there is emanating from it, and that draws the electrons in and holds them in place better. So the stronger attractive force requires more energy to overcome them. This refers to, and so I'm talking about these, okay? This refers to the Q terms in Coulomb's law. So Z effective is equal to the nuclear charge minus the number of what we call shielding electrons, or inner core electrons. Okay, so inner core electrons would be the total electrons minus all the valence electrons. Okay, so your Z effective is your nuclear charge, your atomic number, minus basically minus your valence electrons. Okay, the higher the Z effective, the more positive the nucleus, then the stronger the force of attraction is going to be. So as far as the distance goes, when we're talking about explaining trends and Coulomb's law, let's look at what happens with the distance. Attractive forces dissipate with increasing distance. So the further things get away, the further those charges get away from each other, the smaller or the weaker the force of attraction between them. So distant electrons are held more loosely and thus easily removed than ones that are closer to the nucleus. Okay, so this term shielding, we're just going to talk about it. We're not going to use it a whole lot, but the term shielding refers to electrons that are in the core, not the valence electrons. Electrons in the core shield the nucleus attractive force from the valence electrons themselves. So if there's a lot of electrons, core electrons, that kind of covers up the nucleus so that those valence electrons aren't attracted to the nucleus as much as they could be otherwise. Okay, so this is only when we're going up and down a group. So things at the top of the group react differently than things at the bottom of the group, because things at the bottom have additional energy levels. They have additional core electrons that shield those valence electrons from the pull of the nucleus. This does not work when you go across a periodic table, because they're all on the same energy level when you go across the periodic table. This only works when you're increasing your energy level. So what shielding does is it reduces the attractive force between the valence electrons and the nucleus, making the valence electrons easier to remove. So it reduces your ionization energy. Okay, and again, we can explain, you can use Z effective to explain this, because again, the higher the core electrons, remember Z effective is Z, the charge minus the shielding electrons. If you have a whole lot of shielding electrons minus the number of protons, then that's going to be your Z effective. Okay. All right. Electron-electron repulsion. So we can minimize electron-electron repulsions. This puts the atom in a lower energy state and makes it more stable when we reduce electron-electron repulsions. Because opposite charges attract, like charges repel. So if we can reduce those like charges, those electron-electron repulsions, then we'll be in a lower energy state. More electrons in the same energy level or sublevel repel each other because of the increased charge. You remember, go back to Coulomb's law, our charges are Q1 and Q2. If we have more of those charges, or those charges are bigger, then our force of repulsion is going to increase. So the more charges, the more like charges you have in a particular space, that force of repulsion is going to get bigger and bigger because they don't want to be near each other. Okay, and so this will expand the electron cloud. They'll move so that they get farther away from each other and reduce that repulsive force. I think we're going to come back to this one. No, we're not. Never mind. All right, so practicing justifying these trends. So if our trend, the atomic radius trend, first we need to know what it is, and then we need to be able to know what it is going across, what it is going down, and then justify those trends that we see. So there's there's atomic radius, there's first ionization energy. Let's look at this one. So atomic radius is just essentially is the distance from the nucleus, the distance the nucleus is to the valence electrons. How far is it from the nucleus to the valence electrons? It goes down as you go across the period, and it goes up as you go down the period. So it decreases when we go across, it increases when we go up. No, ooh, that was so wrong. It decreases when we go across, and it increases when we go down. That's the correct way to say it. Decreases when we go across, increases when we go down. So things at the bottom of the periodic table are bigger than things at the top. Okay? Things on the right side of the periodic table are smaller than things on the left. Justification is we have an increased Z effective. As we go across, we have an increased Z effective. By that, I mean we have more protons and more electrons. Okay? As you go across, you're adding protons, you're adding electrons. So adding and added electrons are all in the same energy level. So they're all the same distance from the nucleus. So that Z effective gets increased. The effective nuclear charge gets increased. And that allows the radius to become smaller. It pulls the radius in. Okay, where we increase when we go down. So when we go down, we're adding energy levels. According to Coulomb's law, the distance in the denominator, the distance between those two charged particles, as that distance gets bigger and bigger and bigger, it makes the force of attraction less and less and less. So the radius, as the radius gets bigger, because of the energy levels being added on, the force of attraction gets smaller. So the atomic radius gets bigger. Okay. First ionization energy. Again, it's the energy required to remove an electron from the atom. It increases as you go across because of effective nuclear charge. And the more valence electrons are attracted to the nucleus, that requires more energy to remove them. Okay. The valence electrons become closer to the nucleus, requiring more energy to remove them. So there's more of attractive force between the valence electrons and the nucleus, and because they're closer to it. So that's going to make it harder for them to be removed. And first ionization energy decreases as you go down. Again, we're adding energy levels there. So Coulomb's law, the force of attraction between the nucleus and those valence electrons gets smaller because the distance between them gets bigger. Reduced force of attraction between the nucleus and the electron cloud means it's going to be easier to pull those valence electrons off. Okay, let's see if I can find my slide on electron affinity. Somehow I missed it. Yeah, I skipped it. Let's go back up here to come on. Oh, come on. What are you doing? There we go. Electron affinity. All right, so an electron affinity, again, is just how badly does an atom want to add an electron. It's a measure of how much energy, a change in energy that occurs when an electron is added. So things up here have a very, very high electron affinity because they want to add electrons. They really want another electron. So it increases as you go across, and it increases as you go up. Okay? Let's look at the term electronegativity. Electronegativity is just the relative ability of an atom to attract an electron to itself. So fluorine is your most electronegative element. It really wants to add one more electron. The three most electronegative elements that you need to know are fluorine, oxygen, and nitrogen. And if we look at this diagram, you can see the trend, if it will come up. There we go. All right, so fluorine is the most electronegative element here. Francium is the least electronegative. So it's going to increase as you go up, and it's going to increase as you go to the right. Okay. Again, it's just based on where the electrons are. Fluorine has 7 electrons, has 9 electrons, 7 valence electrons. If it had one more, it would have a full shell, which would make it more stable. So it really wants to gain that last electron. Let's look at a couple of practice questions here. So naturally occurring copper is composed of 2 isotopes. If copper is 69%, copper 63, and 30% copper 65, the average atomic mass would be what? So again, you are going to take your percentage and your mass. You are going to multiply those two things together for each isotope, and then you are going to add the two numbers together. So the correct, you do not need to divide by 2, so A is incorrect. B, you got to consider the percentages, so B is incorrect. Your correct answer is going to be D. C is incorrect because this is not, that's your percent, not your decimal. You need to change that percent to a decimal first. Stop. There we go. Okay, so the next one. Photoelectrospectra show the energy required to remove the first electron from nitrogen and from oxygen. Which of the following statements best accounts for the peak in the upper spectrum being to the right of the peak in the lower spectrum? Okay. All right, so here's nitrogen at 400. Here is oxygen between 6 and 500. Nitrogen atoms have half-filled p subshell. No, they do not. Nitrogen has, there we go, forgot my periodic table. Nitrogen has 7 electrons, so that would mean we have 3. So it does have a half-filled shell, but let's see. The next one, there are more electron-electron repulsions in oxygens than in nitrogen. Electrons in the p shell. Subshell of oxygen provide more shielding than electrons in the p subshell of nitrogen. Nitrogen atoms have a smaller nuclear charge than oxygen atoms. All right, so we're wanting to know why does it take this much energy to remove an element from oxygen, but only this much to remove an element from nitrogen? Okay. Let's see. There we go. The correct answer is D, because there's less effective nuclear charge, means less energy required to remove an electron. Right, so nitrogen has less Z effective, so that makes it easier to remove that electron because it has fewer protons than oxygen does, and so it doesn't require as much, it has that. Okay, go back. So the correct answer is D. There you go. And it is D because the nitrogen atoms have a smaller nuclear charge. They have fewer protons. Nitrogen has 7 protons, whereas oxygen has 8. Okay, because of that, it's going to make it a little easier to pull the electrons off of nitrogen than oxygen. Okay. All right, so an element Z has electron configuration given there. The oxide of this element will have which formula below? So we have 2 valence electrons here. Okay. So that means that it can react with oxygen because oxygen is looking to gain 2 more electrons. So I believe C is going to be the correct answer. Let's see. Yes, C is the correct answer. The electron configuration indicates 2 valence electrons, and those 2 valence electrons would be given up very easily to oxygen, who wants 2 electrons. Okay, so we have first ionization energies of oxygen and nitrogen is best explained by which of the following? Okay, so here's oxygen and nitrogen. So oxygen has a lower first ionization energy than nitrogen, and it's asking why would that be? Why would oxygen have a lower first ionization energy than nitrogen? Differences in electronegativity between oxygen and nitrogen, repulsion between 2 paired electrons in the oxygen orbital causes the first ionization energy to be less. Greater Z effective nuclear charge in nitrogen than in oxygen causes the first ionization energy to be less than that of nitrogen, or a greater atomic radius in the nitrogen than in the oxygen causes the first ionization energy. Okay, well, we know that D is incorrect because nitrogen does not have a greater atomic radius. So we can take out D. Differences in electronegativity. So it's going to be between A, B, and C. So let's take a look at our correct answer. The correct answer is B. Comparing electron configurations of oxygen and nitrogen will allow you to see that oxygen has paired electrons and nitrogen does not. So let's go back to that question. So if you look, the electron configuration for nitrogen is, oh, come on. 1s2, 2s2, 2p3. For oxygen is 1s2, 2s2, 2p4. So there are paired electrons in this orbital. 1, 2, 3, 4. There are no unpaired electrons in this orbital. That makes that orbital more stable. So it is going to be harder to pull an electron off of there than it is to pull this electron off of here. Okay. Which of the following elements would have the largest second ionization energy? Okay. Largest second ionization energy. Well, it can't be A because hydrogen doesn't have one element or one electron, so it can't be A. Let's see, fluorine has 7 valence electrons, sulfur has 6, potassium has 1 valence electron, and then it has a full shell. So it has 1 valence electron, and then you're removing, at that point, you're removing core electrons. So I'm going to say D is the correct answer because it's going to want to give up that first one, but it is not going to want to give up that second one. And the correct answer is D. Both H and K have 1 valence electron, but K has an additional electron shell. So it has more electrons that could be taken if the energy was right. Ionization for the element X, listed above. On the basis of the data, element X is most likely to be what? All right, well, first ionization energy is low. Second one jumps up to more twice that, and then it just continues to get higher there. Aluminum has 3 valence electrons. Magnesium has 2, sodium has 1, silicon has 4. So the correct answer is C. Let's go back and look at our table. If it'll hurry up. There's a big jump between the third and fourth. Yeah. If we look at the numbers, it jumps here, but it jumps much bigger here. So there's a huge jump between the third and fourth, which lets me believe that C is the element because there's such a big jump between that third, taking off that third electron and taking off that fourth electron, meaning this is a core electron. Okay, so we will, you can just go through some of those in the PowerPoint and use them as practice. We're not going to go through all of them, I don't think. Yeah, we're not going to go through all of them. Actually, that is the end of the multiple choice ones. The rest are the free response questions. So, all right, so that is it for Unit 1.